Hey guys, thanks for trying this way. So the idea is that by giving the lecture in a taped format, you guys can take some notes and you can stop and rewind whenever you need to hear things over and over again. And then you can jot down any questions that you have, and what we will do is on Wednesday, we'll spend about the first 10 minutes letting you guys ask any questions that you may have written down or things that you want me to go over from this lecture. But material from this is on the midterm, and the midterm is the week after spring break, so I really need you guys to have attempted this assignment before spring break so that you're really prepared when it comes time for the midterm. So today we're talking about signals, and in particular ECG signal analysis. So this really feeds off of what Peter Katona was talking to you guys about last week. So first of all, a signal for us is anything which carries information. And information comes with a certain frequency, or the numbers of times that something happens per unit of time. For example, the heart beats about once per second, so it has a frequency of once per second. The units for frequency is hertz, which is the number of cycles per second. So the heartbeat is, roughly speaking, 1 hertz. So a 50 hertz cycle, that's 50 cycles per second. If you do the inverse of the frequency, or 1 over the frequency, that reciprocal is the time, or what we call more often the period. And that's how many seconds it takes for one cycle. Okay, so a typical piece of information, a lot of things that we do come in sine curves. So here's a typical wave. And the period can be defined as the time it takes to get from one crest to a second crest. And that would be the one cycle. And the frequency is 1 over the period. Okay, we also often want to measure the amplitude, which is often the intensity for us. That's how strong the signal is. Okay, the top of the crest to the 0 point, that would be the amplitude. Sometimes what we're interested in is peak to peak, from top all the way to the bottom, and that can be called the peak-to-peak amplitude. Okay. There are 2 basic types of signals. Analog signals can be continuous, so it's anything that comes in a continuous fashion. The ECGs that were talked about in class, started off, they had their P wave, and then they had their QRS, and then the little T bump. That's all an analog signal. That's the way it happens in our body continuously. But when we measure, we tend to use equipment, and that's digital signals. They're discrete values. Discrete values happen when we start sampling the data. Okay, so Dr. Katona talked a lot about sampling, so I'm not going to spend too much time on it, but basically sampling is how you go from this continuous analog signal to taking data at specific times. Okay, each of those is a sample, and then plotting those samples as a digital wave. Okay, so we have a continuous function x of t, and we're taking a certain number of samples. The sampling period is the time from here until the end. That's how long we're taking samples for. So it could be a day, it could be a minute, it could be 30 seconds. The frequency of sampling is 1 over the sampling period. So one of the things that we talked about was that you have to be careful that you get enough data when you're sampling. And the Nyquist theorem states that you need to have at least twice as frequent sampling as the frequency of your actual curve. So if you have a 2 megahertz signal, then you need to sample at 4 megahertz or faster. Obviously, the more frequently that you are sampling, the closer to the real data you're going to get, but you're also going to use up a lot of computer space, and we want to be careful about that. Okay, so for example, if we have a sine of 2 kilohertz, so the frequency is 2 kilohertz. In MATLAB, we define a variable f for the frequency. Since we want 2 kilohertz, generally we're going to put in 2000 because we're generally speaking talking about doing things in hertz. So 1 over that is 20 milliseconds, so that's our period. Okay, what we would do is we would define a sine curve, x of t, as being 2 times pi times the frequency times the time. How long are we sampling for? Okay, so this would give us our analog signal. Then if we want to sample, we would use this subscript S is for sampling, so we would use a sampling period 1 of 200. So basically we're getting 200 of these steps, or TS2 2000. So basically this is just a number of samples that we're trying to get. Okay, so we start with a simple MATLAB code, and we can generate the sine. Again, we define our frequency. We know the period is 1 over the frequency. And what that does is it gives us our parameters for our sine curve. We want to go from time 0 to time 5 times t. Okay, so our step size, dt, in this case we want 100 steps. So getting from here to here, we took 100 data points. And we just generate our plot the way we always would in MATLAB. Then we sample our curve. So when we're sampling, sorry about that. When we're sampling, we start with our sine curve that we just generated, right? Goes above and below. This is our original sine curve. But now we say we're doing a frequency of sampling, fs1, and here we're doing 10,000. Okay, so we get our new period, and we define our new t1. It's from tmin to ts1 to tmax. And again, here we define our new sine wave, x1 is sine 2 pi f t1. That's with our sampling frequency. What's the difference? This is continuous, and this one is measuring in steps. Because it's only measuring in steps, we did a stem plot instead of doing a regular plot. And what you can see is it matches up where we took the data, but there's some missing information in between. Okay, so how does this relate to what we've been doing? Well, Dr. Katona spent a lot of time talking about ECGs. So we have the atrial sinus starts off by activating everything. That gives us our little P wave, or primary wave. We have the flat spot when we get to the sinoatrial node where there's a pause. Then the atria repolarizes, and we have our QRS where the ventricle is contracting. And then again, we have to have our ventricles reset themselves, and so that's our little T wave. And we can have varying frequencies of heartbeat. So the first thing we're going to talk about is how can we use the computer to measure the heartbeat? Well, the first thing we do is we measure the intensity of electrical activity over time, and we get our ECG. And what we want to do to get a heartbeat is simply count the peaks. So one of the things we notice is that our QRS is always above 1.5, 1.7. So that's kind of a good cutoff for finding a peak, that you have to have higher than 1.7. So that's what this program is doing. We're basically saying we're looking for peaks. So right now we don't have any peaks. Peak equals 0. Okay. We want to do a beat count. Right now it's 0 because there haven't been any beats. And we do our for loop. So for the time period that we have our signal, if the signal at that spot is greater than at the spot before it, and the signal at that point in the graph is greater than the spot after it, and it's also greater than 1.7, then we found a peak. Okay, so going back to this previous graph, we're looking for this point right here. We don't want everywhere it's above 1.7. We just want the actual peak. Okay, and then what they can do is add to the beat count. So we had beat count at 0. We found a beat. We have a new beat count. And the problem is, in real life, data is noisy. The patient moves. Somebody bumps into the monitoring machine. There's an earthquake and everything shakes. You get noise. We can't help it. Sometimes the noise from the lights overhead can have a frequency that interferes with some of your equipment. So you're always going to get some noise. Air currents, vibrations. Like we said, the electrical power is one of the more interesting ones, that sometimes you actually have to be careful what type of light bulbs you're using. Okay, so what do we need to do with noise? We need to filter it out. We need to get rid of it. So one of the things that we're going to do in a future MATLAB is add noise. One type of noise is white Gaussian noise. Okay, so the way we do that is we define a new vector, we add white Gaussian noise, that's a function in MATLAB. Okay, X is our original signal, and SNR is our signal to noise ratio. Okay, and that's always measured in decibels. So we can add 20 decibels of noise, or we can add 40 decibels of noise. That way we're mimicking real life. Why would you have a built-in program to add noise? Well, if you're planning on filtering data in the real world, you better have a way of testing it and making sure that what you get back is reasonable. Okay, so if we add noise to a signal, now instead of nice clean bumps, we get all this jagged noise in between. Okay, this is with a 30 decibel. Okay, we can also compare using a subplotting our actual to our noisy. So with 30 decibel noise, it's kind of noisy, but you can still see the basic shape, right? This isn't a big deal. This is something that somebody could visually interpret. But what if it gets a little noisier? Okay, here we've already lost our T, and in some cases our P waves. It's one you can kind of see, but it's starting to not look so much like an ECG. We can still easily determine our peaks to do a beat count, but Dr. Katona showed us some really cool things that you could make some diagnoses just by looking at the shape of the ECG curve. We've lost that information down here. So what we're going to want to do is filter it. This is a really noisy piece of data. This one's about 40 decibels. Here you almost can't even tell for sure where you have a heartbeat. Okay, so this is just a program for adding noise. You're not actually going to have to do that. On the homework, we've provided you with noisy data. And the idea is that you're going to filter that data. And you're going to do it two different ways. You're going to write a program using a for loop, and then you're also going to use the built-in filtering function on the computer. That way, when you look at your two answers, you can see what it's doing, and you sort of understand what the filter is doing in the MATLAB program. Okay, so you'll eventually get to see something like this. Our original noisy signal, a signal using a for loop, this is where you do the programming, and the signal using the MATLAB function. And ideally, these two will be very similar and much cleaner than the original signal. Okay, so first, this is just going back to what it did before. We're saying there's a threshold peak of 1.7. If you don't hit at least 1.7, you don't have a heartbeat. So here we're clearing peak detected. That was a variable used earlier when we were counting peaks by doing the if it's greater than the one before it and greater than the one after it and greater than 1.7. We can write a new little program. If it's bigger than the threshold, the peak is detected. Okay, when you have really, really noisy data, that may be all you're doing. If we go back, okay, if we go back here, oops. Okay, if we go back to something this noisy, that may be all we need is, gee, there's a peak in here somewhere. Okay, but here we plot our detected peaks along with our data. And you see it matches up pretty well. We've gotten our detected peak in this area higher than 1.7, and it matches up. Okay, so we need to talk about image processing. Why are we going to do image processing? What's the point? Well, most of you guys, I'm sure, have taken pictures with your cell phone cameras. And I'm sure you've seen that you move your hand, you get a blurry picture. It's too dark out, you have to hold still too long. And these are all things you can filter out. Red eye, right? Your phones do this type of image processing for you. Okay, but you need to understand what's going on so that you can apply it in an engineering situation. So the main things that you're going to do, you're going to enhance an image. Get rid of noise like we were just talking about. If you're looking at an x-ray and it's all fuzzy in the middle, it might be hard to tell if there's a broken bone. So one of the things you can do is sharpen edges or de-blur something movement through a picture. Okay, you can improve contrast. You can brighten an image. Okay, you can also restore images. A lot of times you'll see this going on in police work. There'll be something going on where you didn't get a very good signal. And so what you have to do is sort of fill in the blanks. If you think about the pictures that they take of somebody who's trying to rob a convenience store and pulls a stocking over their head. Why do they do that? It blurs the features. Even when you take a picture, it's really hard to identify that person. But what that is periodic interference. The fabric is creating an interference. You can artificially remove that interference and restore part of the image. It also removes optical distortions. If you're using the wrong type of lens and you sort of get a wider part in the middle and crammed data on the ends. You guys, I'm sure, have all seen pictures like that. And in fact, you can also do image segmentation. This is something that you might do if you have a big field of view and you're looking for one specific object. So you can find a circle or a triangle. So it's kind of like when you guys go into Google Earth and you're looking for your home, right? You start off with this really wide view, you zoom in, eventually you see trees and stuff, you find a clearing in the trees where your neighborhood is, and then you zoom in and you start picking out houses, right? What you're really doing is searching for a shape that looks familiar and zooming in on that shape. And you can actually write a program to do the same thing. Okay, so what is an image processing task? You acquire the image, you take the picture. You pre-process it. That's going to be sharpening up the lines, filtering out the noise. Okay. Then you can segment it. And that goes back into that idea of finding a section that you want to look at, whether you're going to zoom in or you're just going to focus on just one section to clean up the image. Okay. Then you represent and describe the image. That's basically replot it. So you've taken this picture, you've turned it into numbers. You've filtered out the numbers, you've pulled out the pieces you want. You take those numbers and put them back into a picture, and then you can look at the picture and recognize and interpret. So you take an ECG, you filter out, you change it into numbers, you filter out the noise. You look at a time period of about a minute or two. You make sure you have that segment completely filtered. You convert it back into a plot, so now it looks like an ECG again instead of a list of numbers. And then a trained technician looks at it and sees the changes in shape that actually mean something. Okay, so there are applications we already talked about: medicine, law enforcement. In injury, you can use this for quality control. A lot of that is done using computer equipment, and if it's too noisy, they can't actually tell what they've got. Okay, so there are several types of digital images, and we're going to focus really on 3 of them. There's I feel like I missed something in here. Where did we do the filtering? Okay, hold on. I may have messed up where I thought things were. There's 3 types of digital images. There's binary, that's your black and white picture. Grayscale, there's shades of gray, it's not exactly on or off. And then true color RGB, red, green, and blue. Why is it RGB? Because remember, when we're looking at pictures, that's not painting colors, that's light. And with light, color is additive. So red, green, and blue are our primary colors. Okay, binary, black and white. Each individual pixel is on or off. There's only 2 choices, so you only need 1 bit. Okay, it's really efficient in terms of size. It doesn't take much data. It's 1 bit per pixel. Okay, text is like that, fingerprints, things that you don't really care, you just need to see it's on or it's off. But sometimes shading is important. Okay, somewhere where shading is important might be something like an X-ray. X-rays are often in grayscale. You don't need to know the color of everything, but the brightness can tell you something about density. So here, each of your pixels is a shade of gray. So instead of using a bit for each pixel, we're actually going to use a byte. A byte is 8 bits big. So how do we figure out how many points we have? Well, It's 2 to the 8th power, which is 256 possible shades of gray. So each of the bits is on or off in a binary number that goes from 0 to 255. 0 is black, that means it's completely off. Completely white is 255. And then you can get everything in between by turning different bits on and off. And last we have the true color, or red, green, and blue. So here we have that same 1 byte per color. So we have 1 byte of red, 1 byte of green, 1 byte of blue. So we have that 255 possible states, from completely dark to full red, completely dark to full green, completely dark to full blue, raised to the 3rd power for each of the possible colors, giving us about 16 million different possible colors. This is why we like color pictures. You see the world fairly close to how it is. But it's very data intensive. You need 24 bits per pixel, or 3 bytes per pixel. That starts getting to be a lot of data. That's why a lot of the files that you try and send, when you take a picture and you try and text it to somebody, a lot of times they have to compress the file. It's just too much information. Okay? In an RGB picture, every pixel corresponds to a different value, to 3 different values. So it's a 3D matrix, 1 for red, 1 for green, and 1 for blue. Okay, and we can actually use several different image formats. There's bitmaps, JPEGs, TIFF files, and PNGs. Okay, and again, which type of image you use, there's going to be a different file size. Okay, so if you do a binary or black and white, really, really small files, 0.032 megabytes, it's nothing. All the way up to 0.786 megabytes for an RGB, and that's just a 512 by 512 image. That's counting the number of pixels across and the number of pixels down. So think about how good the resolution on your camera is on your cell phone, and think about how much data you're actually storing just to take one picture. Okay, what I want to do is go back to the filtering, and somewhere in here, here we go, the averaging. I skipped over kind of an important slide for what you're going to be doing for your homework. So let's go back and talk about averaging. Okay, so we had our really noisy data here, and we got to this nice filtered signal, and I somehow skipped the program to do that. Okay, so what we're doing is really averaging. So at every single point of data, you're going to take 1 step back and 1 step forward for this program. So this is a window size of 3. That means we're averaging the data point before, the data point we're at, and the data point immediately following it. And so what we're doing here is we create AF, this is our filtered image. We create a vector of zeros, which is the same size as our noisy signal. Okay, and then what we do is we start at point 2. Why do we start at point 2? Because if we started at point 1, there's nothing right before it. So the computer doesn't know what to do, and you get an error. So if we were going to average 7 data points, right, that means we have to go 3 back and 3 forward. You have to start at point 4, because there has to be a point 3 points back for it to average. So what does that mean? It means you lose a little bit at the ends. But you make up for it by having a smoother curve. You filter out more of the noise. So you have to kind of strike a balance between what you're going to lose on the edges and how good a filter you actually need. So this program is an example program for a window of size 3. So for each data point in our original noisy signal, starting from point 2 and going all the way to the end -1. Why is it the end -1? Because again, if you go all the way to the end, you have to do the data point after it, and that data point doesn't exist. So that's going to produce an error also. So what you're going to do is you're going to define your new matrix, right? You have filtered data. Right now it's all zeros. So you're going to replace data point I with the average, simple arithmetic, the point minus 1 plus that point plus the points after it, and you divide it by 3. That's it. And then you just plot your data. In the program, you're plotting over 5 points instead of over 3 points. So the difference there is you have to figure out where do we start, what is our final length, and then you have to program it correctly. Okay, once you're done with that for loop, you can make a plot. So you can make subplots so that you can show your actual noisy data. You can show your filtered data, and then you can do another one which is filtered using the MATLAB function. The MATLAB function is actually really easy, straightforward. It's this one right here where it says direct filtering. You give it the window size that you're supposed to. You define your new function and you tell it what to do. Filter ones, 1, and then your window size. Okay, that's all you have to do. If you need help with that part, the help file is pretty straightforward on the MATLAB function. If you need help programming the for loop, then please get in touch with myself or Nima. I can be reached by email as Ken Nima, and since we have spring break a week from today, your assignment is actually due on the 17th by midnight. So you will see us on Wednesday. Nima will have office hours on Friday. And then you have all of spring break for you procrastinators out there, but this isn't one you want to procrastinate on. And then you can ask us last-minute questions in class on the 17th as well. So I really want to thank you guys for being patient and for trying this so that we don't lose a class. See you on Wednesday.